Yeah, okay.
Yeah. So yeah, that was quite something. If you need Sherban's contact details, I can pass them on to you. That's not a problem. And I guess we are ready to commence our oral session number 2. We are 10 for people watching live on YouTube. We are 10-15 minutes behind time, so apologies for this. Our next speaker is my colleague from the University of Portsmouth, so Robson Christie. I invited you, sir, because you were involved, as far as I know at the time, in quantum computing research. So I was looking for a quantum computing, quantum information presentation. But I think from what I understand, you and JU, you had some cool results on quantum simulations of these chemical transition rates. So you choose to present something slightly different, but I'm totally happy with this.
No,
Thank you
it's a
so
quantum
much.
computer algorithm.
All right then. So, but
Yeah.
thank you so much for this, and I'm gonna mute myself, cut the microphone, and I need you to wait 5 seconds so I can start the recording. Thank you, thank you.
Okay. I think that's been 5 seconds. Hi. I'm Robson Christie. I was a research fellow at the University of Portsmouth. In 3 weeks, I'm moving to my next postdoc in South Korea at Busan National University. And I'm presenting some work that I did with my collaborators, Kyung-hoon Baek, Jong Hao Bang, and Jae-woo Ju. Jae-woo is at the University of Portsmouth, and the other two are at Yonsei in South Korea. Um, and yes, quantum simulation, it, it's a confusing name because a lot of the time people are simulating quantum systems. But in this context, it means like how to simulate on a quantum computer. Um, okay, yeah, I have to use this free PowerPoint and it's messed up the order of these. But so why transition rates? So they're just it's it's just a when you do a quantum computation, at the end you get a readout on the spins, and uh, the most efficient algorithms use the fewest spins as readouts. So transition rate is just a number at the end. So unlike classical numerical simulations, you tend to have to just deal with your output at the end is just a string of bits. Uh, your observables. And the transition rate is quite an important one in chemistry. So we thought we would try and come up with a scheme to simulate this on a quantum computer. So, uh, yeah, so the rate constant, K, state A to state B, underpins barrier crossing diffusion and relaxation. Um, and real chemical, so usually uh, classical molecular dynamics uses GPUs to simulate large classical systems, but and they ignore quantum effects. Uh, but there are some interesting systems we'll talk about later where uh, the quantum effects are present at room temperature in wet environments, etc. So yeah, so this is kind of motivation. Um, so where's the so if I go to the Lindblad equation, so this is basically an extension of the Schrödinger equation to to quantum mechanical density operators or quantum mechanical systems. And the Schrödinger, okay, can you see? Hopefully you can see my mouse. So this is the Schrödinger part, and these are the environmental effects. Um, so just to the quantum analog of the Langevin equation, which is basically the standard the standard form of Brownian motion, can be written. as one of these equations, Lindblad equation. Um, and it's not one equation in particular, but it's just a family that satisfies these properties in that the current noise doesn't depend on a long past history. It just depends so that the dynamics at time t only uh, are affected by the state at time t. Um, and it preserves the hermiticity, um, which just means that you have uh, real positive probabilities from the positivity, and it preserves the trace, so the sum of the probabilities adds up to one at the end. So before we define quantum transition rates, how are we going to define them classically? If you imagine a coordinate space represented by this double well, and you define regions A and B, and then on these regions, you define functions of the position such that for the indicator function of A, it's 1 when the coordinate is an A, and for the B, it's the same story. Um, and a tool to describe the transitions is like a correlation function. So what this means is if you start in basin A at time 0, what is your probability to be in time t to be in state B at time t? So you imagine if this is perfectly symmetric, and you leave this Brownian particle for an infinite amount of time, this will approach something like 50-50 if this is symmetrical. If B is a bit shallower, then it's going to end up favoring A at given infinite time. Um, so the correlation functions tend to look like this. So initially, you have a lag period where there's not been enough time for anything to escape over to B. But then, after a given amount of time, you have this thing called linear response, where the flux coming back from B is balanced by the flux coming over is balanced coming by the flux coming out of A, but there's more particles in A. So overall, you're still approaching equilibrium. And the derivative of this correlation function flattens out in this region. And the value the derivative takes, we define as the transition rate. Um, so the equations might look a bit intimidating, but quantum mechanically, this is an integral over basically you're just projecting the space of quantum mechanical states onto your region A. And it's basically the same idea as the classical case. And the expression for the transition rate is just analogous to the previous slide, but in terms of quantum objects, like the projection operators at time 0 on A, the projection operator on time B, or the derivative of it at time t. So we came up with a scheme to give. So I'll explain these individual elements here. So this is a high-level sketch of the quantum algorithm. So when you program a quantum computer, you have your qubits on the left, your initial states. So this is a control qubit. So it's just a quantum 0 or 1. This is our representation of the state, the projector B, which is also a Hermitian operator, so it can be represented as a quantum state. Same with A, and rho equilibrium is kind of the equilibrium state of the system. And this is, our tunable parameters are this phase chi on our control. These controlled, so a controlled projector here n, and that means that if this is a 1, this applies. If it's a zero, it doesn't apply. If it's a one superposition of one and zero, it both applies and doesn't apply. Uh, so and this is a controlled swap. Um, but basically, what happens is at the end we measure this. We only measure this qubit, this one qubit here, and you do this many times. So you get an answer zero or one, and you average this answer, and you'll get a number between zero and one. And this is the derivative of the correlation function in the end that I just mentioned. Um, so uh, yeah, and interestingly, for these open system quantum Brownian processes, they're what are called non-unitary. So they don't preserve occupations of different quantum states. They have a fixed state, kind of like how things tend to equilibrium. So a unitary process will keep populations intact, but in the basis of it'll keep the populations of different energy states intact, but non-unitary processes don't. So how do you simulate this non-unitary process on what is a unitary device, which is say like a quantum computer? Um, so it's quite interesting. So you have your density operator here. So we didn't come up with this algorithm. This is from 2016. Um, and you have this joint this unitary that acts on. Let me just move the zoom bar so I can see. Yeah, so you have a zero state here, and the density operator. Sorry, 1 second. My wife forgot her keys. I'm just letting her in. That's what you know. Yeah. Ah, cool. Yeah, so you have a unitary operator here, and it entangles your system with a zero qubit. And then after the entanglement, you trace out. And what trace out means is you measure this qubit and you basically throw away the answer. Uh, so, and this gives you kind of instead of a superposition of different states, a classical mixture. So think of it as like a coin toss, a classical coin toss. Um, and so uh, a really simple example of what's called a metastable state. So a metastable state is like you can think of a double well in that if this double well is very deep and transitions are rare, it spends the vast majority of its time in either state A or B, and a very small amount of time transitioning between A and B. So the simplest quantum mechanical metastable state is basically think of a single spin that has a magnetic field along the y direction, and what this does is it causes the state to rotate about the y-axis. And if you have a kind of weak measurement in the z basis, so what happens after each measure after the measurements is you end up on either the poles of this block sphere. So so if you're close to state Z and you measure if you're close to the zero state or the top of the block, the North Pole, then when you measure the Z, you're overwhelmingly likely to be found back at the North Pole. But say you are at the North Pole, you won't just stay there. The magnetic field will cause you to start moving across the Y. Okay, I hope people can see the cursor. Um, yeah, so I can draw. Yeah, you'll start
No, we can see it.
okay, cool. Um now I'll get Okay. So, and you'll start to move and give this incredible amount of time, and the small probability of being found at the South Pole will eventually happen. So it's metastable in that it's uh let me okay, cool. So the Hamiltonian is just some field strength times the Y operator or the sigma Y operator. Um, and the measurement operator is in the Z basis. So our two projectors are the North Pole and the South Pole. Um, and what's nice about this system is it's analytically solvable. So what I'm going to so our experimental work, uh, we could easily validate that this system was working. So we we ran uh, we ran the algorithm on an IBM quantum computer, um, and and it used 6 qubits in order to implement this. Um, and the transition rate uh, the transition rate algorithm was actually quite good considering I only had a few Gmails worth of free trials at IBM Quantum. Um, so you have the ideal 6 qubit result in as this red dotted line, and these were our results from IBM's actual quantum machine. So it was quite cool that it was actually, even though they're quite modest results and there's an analytic solution, that they were actually were able to demonstrate that this works. Um, and we tested in quantum simulators and found that the residual goes to zero. Um, by quantum, so we tested in classical simulations of quantum computers. So really, as the hardware, so the hardware's not very far. Well, for like general purpose computing far along, but it's a cool proof of concept. Um, cool. So, uh, so yeah. So why make something like this is if you one thing people mi often misunderstand about quantum computers is if you were to so say you have say we go back to this circuit. If you had to measure all five, or say all five of these channels, and get all the qubits, you'd be sampling for so say there's 5 qubits here. You'd be sampling from a 2 to the 5 element distribution, and every time you run, it's stochastic. So you'd have to do many trials in order to get a converged answer. And if you have to measure all of the qubits, you've almost lost almost all of your potential quantum advantage. Um, so the most efficient way to do something like this is to, as we've done, where you uh, may not be the most efficient algorithm, but we're using one readout qubit, and our transition rate uh, is determined by the expectation value of this one qubit. Um, so yeah, so when we did something like this, we ran 10,000 for each data point. We have to run 10,000 of these shots. Um, and in total, this is about takes about 1 second on an IBM machine, not for each shot, but all 10,000 takes about 1 second. Um, and we did 5 trials in order to get the spread and put an error bar on it. Um, and the rates are very small. But that's kind of this the problem with calculating rates by brute force is if you're just doing trajectories, uh, so say you want to do a trajectory, you have to do a very long numerical integration just following a trajectory that primarily sits in one of these basins before you actually witness an event. um, which is one of the strengths of this linear response theory, is that you simulate an ensemble for a very short amount of time, or a density operator, which is an average over stochastic quantum trajectories. Um, and even when uh, not many of them have passed through, so say we go back to this plot here, so say a very small fraction have passed through, so say like 8% here. Um, yeah, cool. Um, so yeah, with epsilon shots, the single observable only needs 1 over epsilon shots to get a good statistical estimate. Um, cool. So where would something go beyond this toy example? And we've done this on quantum. So IBM's got a platform called Qiskit, and you can run classical simulations of quantum computers on your GPU, and it uses some clever tricks to not simulate the full Hilbert space of these systems. Uh, but yeah, so say you have 5 qubits defining your system, and you define a double well potential here. So each and if it's between 0 and 1, then it's the n n decimal binary decimal uh, element of the Hilbert space is your your basis vectors, or your grid points. And this simulation took 16 virtual qubits. Um, and we got some interesting non-trivial dynamics of the correlation function. So this merges like a mixture between the Brownian hopping and also tunneling uh, into how does this particle escape this world minimum here. Um, and say you scale up this up to 3D, you see how this and you allow all-to-all couplings, how a problem like this might become infeasible. I mean, this is just about doable on a GPU, and this is a very simple, an incredibly simple toy model, really far away from some complicated things that we actually see in chemistry. Um, oh, and maybe I went a bit fast, so we might have a lot of time for questions or the next speaker. Um, so basically, transition rates uh, boil down to uh, expectation values of these different quantum circuits. We tested it for a toy model on a real quantum computer, um, using a quite modest amount of resources or free trials. Um, and yeah, so yeah, there's nothing that says you couldn't uh, scale the algorithm up. There's obviously hardware limitations, but it's kind of an example of something that's not a synthetic benchmark that we tried to do, where we tried to do something that was actually useful in for chemists. Uh, and yeah, it's very hard to compete with classical hardware because it's very, very good. Um, but yeah, it's just more of a proof of concept. Um, so yeah, so if I go back to when I said hydrogen and metals at the end, um, I can't go back. Where's the Yeah, so an example here is small hydrogen molecules, even at room temperature, are thought to undergo a kind of quantum diffusion through this lattice, uh, and it doesn't follow your typical Brownian motion. And there's kind of like a maybe a decoherence assisted, a mixture of tunneling and barrier hopping going on. And this happens even in quite often in just metal pipes and like at room temperature. And it embrittles them. So that's one possible industrial application of these types of simulations. Um, cool. And we got any cool? Yeah, cool. And I guess that's my talk. So thank you for listening. I probably went a bit fast. Um,
Thank you, Rob.
cool.
We are over time actually, but not because
Oh,
of you.
really?
It's because no, it's because of the previous previous talks. Yeah.
Yeah.
So thank you so much. I have to confess I did not understand everything, but if you could go back to the double well
Yes.
diagram, because I've done some work in this area using non-equilibrium statistics, Pauli master equation, and you get a lot of physics out of this. Actually, I managed
Hmm.
to derive an equation for polarization dynamics. In fact, a lot of magnetics and micromagnetics come from this from this approach, a non-equilibrium approach to the transition rates using
Hmm.
Pauli master equation. So in the classical approach, basically you have an energy barrier and you have
Yeah.
thermal activation or some kind of other form of energy. For example, if you apply field,
Yeah.
you move the energy barrier, you move one of the well up or down
Yeah.
using external fields, and thermal energy acts as an activator over the barrier. When you take the quantum system,
Hmm.
what is the physical process? What physically happened there? Do you have
So
tunneling through the
yeah.
barrier,
So
or do you have jumps like the classical jumps?
so you have both at the same time, and they kind of intermingle with each other. So the tunneling rate might be quite low between the two minima here. But if the particle was classically excited up to the rim, but didn't quite have enough energy to go over the top, it might then tunnel
Mhm,
across the gap and then classically fall down. And the point of these like quantum simulations is to capture this behavior because it's also there's something that happens quantum mechanically with these heated systems where you have like Arrhenius law where the is exponentially sensitive to the height of the barrier um, and over the temperature. And classically, you'd expect the rate to go to zero as the temperature goes to zero. But quantum mechanically, you find that it plateaus, and you have this region where you don't have a. So as the temperature increases, you get kind of like Arrhenius law, but
mhm,
there's a sweet spot where it transfers from a plateau to Arrhenius, where you have a mixture of these two effects. So the example would be classically almost hop, not quite enough energy, and then tunnel through the small barrier. Um, and these Lindblad systems really, or these quantum Brownian motion systems can capture this.
Okay, so it reminds me of the zero Kelvin oscillations in quantum mechanics.
Yeah.
Yeah. So yeah, it's quite different than the classical case. But yeah, classically, you can get a lot of physics out of this, and it actually matches experimental data big time.
Yeah, yeah. It's like on each to their own. They're not that hard to simulate, so it's not
Hmm.
hard. It's you can simulate the classical system really easily, and the quantum mechanical system at zero temperature is quite easy. It's harder, but
Hmm.
it's a lot easier than the finite temperature quantum system. And
Yeah.
these things are really hard.
Excellent.
Uh,
So let me just allow our participants to ask any questions. Now, everybody can open your microphone, please, if you need to ask a question. Camera, microphone are available to you now. Rob, thank you so much, and congratulations for the postdoc in South Korea.
Cheers.
Good luck. How
Thank
long
you.
is that? How long you're gonna be there?
So I've got 5 years as on the contract, which is quite good.
Oh dear, dear. Be careful because in my experience, 3 years is about the cutoff. After three
Yeah,
years, you move somewhere and it becomes home. So you
yeah,
might never come back from South Korea if you stay that long.
yeah,
I'm telling you, is
yeah,
yeah, is I mean I've been there. So
yeah,
yeah, I never
yeah.
expected to make UK my second home, but you stay long enough and it becomes home. So
Mm,
about 3 years is my,
yeah.
the sort of like the cutoff time. Uh,
Five's good if you
but
find you love it.
but
But
this is a good postdoc, a decent time.
um,
5 years
yeah,
is not is quite unusual actually.
yeah.
My longest was 3 years. So yeah, well done, well
Thank you.
done. Okay, I see we have already people ready to ask questions. Anybody? Um, I guess we have no questions.
I
Um,
just
Rob,
explained it really well then, I guess.
no, or maybe it's too
Yeah.
complicated.
Yeah.
I need to revisit this and look
No,
again at
no.
what you did because it's not.
Cool.
I'm not doing everyday quantum computation mathematics. Rob, thank you so much
Thank
for
you.
this. Best of
No,
luck
thank you
with
for
your
having me.
postdoc. And yeah, I need to think about this. I need this
Um,
double well because of information theory is the non-equilibrium discussion around the information states. How do you discuss that? How do you treat that? You go the quantum way, you go classically. I don't know, and it's a complicated business. I need some help maybe at some
sure,
point
yeah.
to look at
Uh,
this. Yeah, but
cool.
thanks a lot, and we are ready to move on to the next speaker. So what do I do now? Let me I'm not sure what is why it looks different. My interface. Something changed. Record settings. Um, so anyway, our next speaker is I hope I'm not butchering the name, is Johann Pascher. I have a video
Okay.
recording provided, a pre-recorded talk, but I think Johann is available here. So let me just make you co-host. Confirm. So hi Johann. Do you want me to run the recording or do you want to run the talk yourself? It's your choice. The
Yes,
file is ready to run.
yeah, please run the recording. Yes, please.
Run the recording. Okay. And so in that case, I'm going to remove the co-host so we don't have your image available there. Settings. Something changed here. I don't understand why my interface looks different. So revoke co-host. Share. I need 1 second, please, to locate the. Yeah. So I hope you are receiving the video feed now.
It just says Information Institute has started screen sharing, but it doesn't show a feed yet. Um,
Hmm. this was not
Slide 1. Welcome. This is FFGFT, the fractal field geometric fundamental theory. Over 6 parts, I'll walk you through a single, slightly stubborn idea that the whole zoo of physical constants might come from one number and one shape. Part 1 lays the foundation. We'll talk about why physics, deep down, is about ratios, about how things compare, rather than about absolute quantities, and we'll meet the one-dimensionless parameter that the rest of the theory leans on. Let's begin. Slide 2. Everything starts here with one number. We call it Greek x, that's the Greek lowercase x letter, and it's tiny, 4 divided by 30,000, which is 1 over 7,500, roughly 1.3 times 10 to the minus 4. From Greek x we get the fractal dimension of space, written df equal to 3 minus Greek x, so just a hair under 3, about 2.999. Now honesty up front, the form of Greek x, the 4/3, the symmetry, the way the torus winds, that's derived from geometry, not guess, but the size of it, the 5 to the 4th hiding in that 30,000, that's an input, anchored either in music theory or in the Higgs sector. The theory says so openly. It treats its own foundations as critically as it treats anyone else's. Fundant. Slide 3. Here's the heart of it. Time mass duality, T tilde times m equals 1. T tilde, that's an intrinsic internal time. The little tilde just marks it as the theory's own time variable, and m, the mass. They're locked together inversely. Heavier things carry faster internal clocks. This isn't about clocks on your lab bench. It's about how time and mass get bundled together when you wrap space up into a compact shape. Picture a 4-dimensional donut, the T4 torus, with 4 circles. One of those circles carries mass and time at the same time. Not one circle too many, not one too few. And it means E equals mc squared and plane E equals m are saying the exact same thing once you realize c, the speed of light, is just a conversion factor between two systems of units. Slide 4. This slide is the method in a nutshell. The standard model, our best current theory, has more than 19 free parameters. Every one of them is measured and plugged in by hand, and each carries units that quietly hide a choice of convention. Ask why these values, and the honest answer is, no idea. That's out of scope. FFGFT splits the job into 2 layers. Layer 1 is pure ratios, mass ratios, coupling ratios, the Koide number, all parameter free, unit free, and exactly computable. Layer 2 is the single handshake with the real world. Pick one reference, say the electron's mass in kilograms, and every ratio turns into an absolute number. The point is that the ratios are the actual physics. The absolute numbers are just ratios plus a choice of yardstick. Point. Slide 5. Let's strip physics down in 2 steps. Step 1, the classic move physicists already make. Set h bar, c, g, and kb all equal to 1. That's Planck's constant, the speed of light, the gravitational constant, and Boltzmann's constant. They're all conversion factors, and setting them to 1 makes them vanish. Step 2, the bolder one, even alpha, the fine structure constant, about 1 over 137, the strength of electromagnetism, can be absorbed into how we define charge. So what's left after both steps? Just dimensionless ratios and Greek x. Everything that survived is intrinsic physics. Everything that disappeared was bookkeeping necessary in the lab, but not a law of nature. Slide 6. A natural question, if you're juggling fractal geometry, don't you need messy correction factors everywhere? Mostly, no. In ratio land, the calculations are exact. A small fractal correction, k-frac, about 0.986, which is 1 minus 100 times Greek x, so 100 recursion levels deep, only shows up when you convert to real SI units. And compactified time here is completely static. The flow of time comes from traveling through the geometry, not from the geometry itself. Where you genuinely need the bridge constants, C and H bar, is when a lab measures meters, seconds, and kilograms. Fun fact, the 2019 reform of the SI system fixed C, H bar, and KB to exact values. The theory reads that as the establishment quietly confirming these things really are just conversion factors. Slide 7. Here's an old headache. The gravitational constant G defines the Planck length. The Planck length shows up in quantum gravity. Quantum gravity then constrains G. The definitions chase each other in a circle. FFGFT's diagnosis, that circle only exists because these are unit carrying constants. They're all conversion factors for one underlying structure, so of course they seem mutually defined. The cure is simple. State everything as ratios which need no units at all, and the circle just dissolves. One geometric input, Greek X, and a web of derived ratios. That's the whole toolkit. The payoff, alpha and G, stop being fundamental mysteries and become derived quantities. In natural units, G equals Greek X squared over 4 times me, the electron mass. Slide 8. Slide 8. Let me show you the whole chain, left to right. You start with Greek X, the geometric input. From it you get G equals Greek X squared over 4 times me, gravity from Greek X and the electron mass. From G you get the Planck length Lp by the standard textbook formula. Multiply that by Greek X and you get L0, the sub-Planck length, about 2 times 10 to the minus 39 meters. That's the only relation that scales as plain Greek X to the first against the Planck length. And from there, every remaining constant follows. The honest bit, every single step is either a ratio statement or an openly declared unit conversion. Nothing gets smuggled in. Slide 9. So what about Einstein's famous equation? FFGFT says E equals mc squared and the bare E equals m are the same statement, just in 2 different unit systems. The c squared, the speed of light squared, is a conversion factor between 2 ways of measuring the same thing. Nothing more. The real content is just that energy and mass are the same. The factor is bookkeeping. And once you separate intrinsic time, t tilde, from ordinary coordinate time, even time dilation comes back out cleanly, with no paradoxes attached. Slide 14. Let's be fair to the standard model first. It works beautifully. But understandable? Less so. More than 19 free parameters, all fitted to experiment, none explained. 3 separate gauge sectors, each with its own coupling machinery, bolted together by hand, and 0 answers to the question, why these particular values? By construction, that's just outside its remit. Even the Higgs mechanism, brilliant as it is, adds mass without adding understanding. The mass values stay as input. FFGFT's claim is bold. The same phenomenology can be organized around one single scalar deviation field living on the torus. Slide 15. And here's that radical compression on a single line. The Lagrangian, call it script L, equals epsilon times the derivative of delta m squared. Let me unpack the symbols. Delta m is the field. It's the mass deviation. How much the mass departs from its baseline, point by point. Epsilon is the single coupling, and it's fixed by Greek X. Everything else is just the geometry of the torus. So particles aren't separate fields anymore. They're winding and knot patterns of this one deviation field. Antiparticles? No mirror copies needed, just the same pattern wound the other way. And the Higgs isn't an add-on, its job is folded into how delta m interacts with itself. The slogan, no particles, only field knots. Slide 16. Now, for contact with real quantum field theory, you flesh that out into 3 terms. The kinetic term, 1/2 the derivative of delta m squared, that's the field's motion. The mass term, minus 1/2 mt squared, times delta m squared, where mt is the mass scale of the deviation field. And the interaction term, gt times ci bar, ci delta m, which couples the field to the fermions, ci and c bar, are the Dirac spinors. the standard description of matter particles, and GT is the coupling strength. From this you derive proper Feynman rules, which means quantum corrections you can actually compute, not just postulate. And the numbers loop right back to the ratio layer from part 1. Geometry and Lagrangian tell one story. Slide 17. Once that, you might ask, why keep two different descriptions around? Isn't that redundant? Here's the thing. The geometric form lives on the torus and speaks in windings, phases, and ratios. It's ontologically primary, it's what the theory claims is actually true about the world, and it's ideal for exact parameter-free derivations. The field-theoretic form lives in flat space-time and speaks the language of quantum field theory. It's pragmatically indispensable. It's how you connect to detectors, scattering experiments, and the existing literature. Keeping both isn't redundancy, it's the declared bridge between what is and what gets measured. Slide 18. A neat trick in 3 steps. Step 1. Rewrite, you reformulate the Dirac equation so the mass parameter gets replaced by ratio expressions in Greek x. Mass becomes derived, not fundamental, no free parameter. Step 2. Verify. Document 54 runs the full numerical table, checking every replaced parameter against its real measured value through the declared conversion layer. Out in the open. Step 3. Interpret. The first part of document 53 is pure, parameter-free ratio physics. The second part adds the single SI reference. That separation is just the 2-layer structure from part 1 in action. Slide 19. What? Now a genuinely striking result. You can write Greek x as lambda h squared times v squared over 16 pi cubed times mh squared. In words, lambda h squared. In words, lambda h is the Higgs self-coupling. V is the Higgs vacuum expectation value, the field's resting value, and mh is the Higgs mass. Plug in the measured electroweak numbers and you get about 1.3 times 10 to the minus 4, which matches Greek x. That's a completely independent check from a totally different sector, and it lands. Honesty note, an earlier version had the wrong prefactor, 64 pi to the 4th. It was corrected to 16 pi cubed and logged openly as correction, K1. This Higgs agreement is the strongest cross-sector check in the whole corpus. Slide 20. Watch this chain, no free step anywhere. You start with the T0 Lagrangian. Its self-consistency condition admits exactly one-dimensionless solution, so Greek x is unique, not chosen. From there, G, the gravitational constant, follows as a derived quantity. From G, you get the Planck length, and the Planck length times Greek x gives L0, the sub-Planck minimum, about 2 times 10 to the minus 39 meters, smaller than the Planck length by that factor of Greek x. One important clarification, L0 is not a black hole radius and not a distance you could ever measure. It's a structural flaw built into the geometry. Slide 21. 2 documents, 2 modes. Document 1299 is the simple route. It rewrites the whole dynamics at textbook level. 1 field, 1 potential, 1 coupling. The goal there is to make the compression auditable, in the spirit of, if you can't say it simply, you haven't really understood it yet. Document 67 is the mathematical spine, the updated time-mass Lagrangian foundations, with the duality T tilde times m equals 1 implemented right at the level of the action. It connects the field picture back to the geometric picture, and the bridge is checked in both directions. Slide 24. The 3 charged leptons, electron, muon, tau, each get 2 numbers. For the electron, an invariant Re of 4/3 and a Greek x power Pe of 3/2. For the muon, R mu of 16/5 and P mu of 1. For the tau, R tau of 25/9 and P tau of 2/3. The R's are rational invariants, straight from the torus geometry. The P's are powers of Greek x. Nothing is fitted, and the three generations are linked by that same ladder ratio, Q equals 2/3. They're not three independent things, they're harmonic overtones of one resonator. Honesty log. The tau prefactor was first 8/3, then corrected to 25/9, documented as correction, K2. The Croidy number comes out as 0.6677, computed, not fitted. Slide 25. Alpha, about 1/137, has puzzled physicists for a century. Here is derived from the structure of Greek X as a verification, not a starting point. Heard, if you like, as torus harmonics. Note that H bar and C only show up as SI conversions. The dimensionless core of alpha is geometric, not a constant of nature, but a ratio statement. So alpha changes status from fundamental mystery to derived ratio, exactly the same demotion G got back in part 1. Feynman once said he'd love to know where 137 comes from. FFGFT's answer, torus geometry plus Greek X. 33. Tried 33. Let me give you the lay of the land, about 25 documents, in 5 clusters. Foundations, quantum field theory and quantum mechanics, renormalization, the ultraviolet catastrophe, non-locality, Bell, the no-go theorems, that apparent instantaneity, and the topology that explains it. Formalism, the Hilbert space translation, 4 extensions, and quantum graphity, shown as a special case. Computing, a T0 compiled quantum computer. Tests, Ising machines, qubits, Shor's algorithm, and more. And interpretation, 't Hooft's cellular automata, Markov determinism, the core principles. That's the territory. Let's visit the highlights. Slide 34. Here's a quiet but lovely result. When you quantize the deviation field, delta M, on the compact torus, the sums over modes come out finite all by themselves. No regularization, no juggling counterterms. Standard quantum field theory has to impose an arbitrary high-energy cutoff to tame its infinities. Here, that cutoff becomes the natural scale of the geometry. L0 ends the integration. Compactness does the work that regularization schemes only simulate, and the ordinary Schrödinger dynamics of quantum mechanics emerges in the low energy limit, not as an axiom you assume, but as a consequence you derive. Slide 35. Now something that sounds exotic but is actually elegant. The spectral dimension, ds, basically how many dimensions a tiny random Walker feels, flows from about 2 at small scales up to about 4 at large scales. And when that happens, gravity becomes renormalizable in the ultraviolet, the high energy regime. This isn't an extra assumption, it falls out of the time-mass duality and the fractal dimension. df equals 3 minus Greek x. Other serious approaches, asymptotic safety, causal dynamical triangulations, Horava gravity, all show a similar flow. The difference is that FFGFT derives it instead of postulating it. And where the dimension flows, the old classical infinities soften, which points at a geometric way out of the black hole paradox. Slide 36. Let's talk about the elephant in the room, Bell's theorem. FFGFT does not try to wriggle out of it. Bell's theorem is mathematically airtight, no hidden flaw claimed. The loophole-free experiments are real, and their statistics are reproduced exactly. Cochin, Specker, which rules out assigning fixed values independent of context, accepted too. So where's the exit? It's one specific assumption, measurement independent. On a compact torus, the settings of your apparatus and the source actually share topological structure, so the premise that they're statistically independent need not hold. That's a declared structural exit, not a conspiracy theory. The correlations are carried by the geometry and the predictions stay identical. Slide 37. Right. So why does entanglement seem to act faster than light? Picture 2 particles, A and B, as parts of one closed structure, with no signal path between them. What looks like instant action at a distance is really you reading out a global constraint of the compact geometry, but reading it locally at each end. Nothing actually travels at the moment of measurement. The correlation was already woven into the winding structure when the pair was born. No information is transferred, you're just resolving a shared structure. Relativistic locality is preserved at the level of the dynamics. Only a description that ignores the topology manufactures the paradox, and this, honestly, was the founding motivation of the whole project. Instantaneity as an artifact of description, not a real physical phenomenon. Slide 38. Now, can FFGFT and ordinary quantum mechanics actually talk to each other? Completely. There's a full dictionary. States, operators, every quantum gate, the torus coordinates, written z, r, and theta, translate into the usual Hilbert space amplitudes, alpha and beta. Tensor products, entanglement, Bell and GHZ states, all fully translatable. Measurement gives statistical predictions identical to the Born rule. Time evolution is Schrödinger's equation in the low energy limit. So what's the bonus? The plain Hilbert space picture has the tools but no values. It can't tell you Greek X, the fermion masses, alpha. FFGFT delivers both the tools and the values. It explains why the formalism works, not just that it works. And the translation is bijective, lossless in both directions. Slide 39. Beyond the standard picture, 4 genuinely new features. 1. A deformed version of the spin algebra. SU2, it picks up a Greek X deformation, with ordinary SU2 as the limit when Greek X goes to 0. Tiny corrections at high energy, identical physics at low energy. 2. A new discrete quantum number born from the torus's periodicity with no counterpart in standard quantum mechanics. 3. A fractal mode structure. The mode functions carry the fractal dimension. df equals 3 minus Greek X, so the spectral dimension shifts with scale. No flat Hilbert space can reproduce that exactly. And 4. Topological phases. Winding modes generate phase factors with no analog in ordinary quantum mechanics, potentially measurable with precision interferometry. Slide 40. And finally, hardware. In a T0 compiled quantum circuit, the gates are derived from the torus mode structure, not from abstract unitary matrices, but from the underlying geometry. Now, the theory predicts a tiny deviation in the Bell test value, delta C, H, SH, of order Greek X, about 10 to the minus 4, which sits below today's quantum computer noise. Not yet measurable, but testable in principle. That's a real prediction, not a trick. For context, in May 2026, IBM's Heron R2 chip measured a Bell value of 2.74, about 97% of the maximum quantum bound. That's not the T0 signature, but it shows the circuits run and the hardware works, and the implementation factored numbers up to 143 with a 100% success rate. The geometry to gate connection is established for the first time. Slide 41. And now the framework meets real machines. 3 threads. First, Ising machines, documents 161 and 162. Coherent Ising machines read naturally as native optimizers in the T0 picture, and we lay the quantum mechanical optimization strategy side by side with the coherent Ising machine 1. Second, qubit anatomy, documents 173 to 175, quantum dots, spin qubit control, and the question of what actually lives between the 0 state and the 1 state. Read through the state spaces of the torus. Third, Shor's algorithm with photons, document 176, running Shor without a conventional qubit register on a photonic platform. None of this is offered as proof that the hardware confirms the theory. The point is narrower and fairer. The framework already speaks the language of the machines people are building, and the dialogue is written down document by document. Slide 42. Slide 42. Where does this sit among other interpretations? 2 neighbors are worth naming precisely. The cellular automaton interpretation shares the spirit, a deterministic substrate underneath quantum mechanics. But the substrate is different. It uses a discrete cellular automaton lattice. Ours is the continuous fractal torus. The dialogue is documented and the differences kept sharp, not blurred. And quantum graphity turns out to be a subset. Its graph dynamics embed inside the mode structure of the torus, so it sits cleanly within the framework rather than competing with it. The habit here is the same one as everywhere else. Locate the neighbor exactly, say what is shared and what is not, and keep the comparison honest. Slide 45. The whole corpus is organized into 3 honesty layers. Layer 1, the core derivations, things proved straight from Greek X, the lepton structure, the Coide number, the alpha relation, the 2/3 ladder, fully recomputable. If something breaks here, the theory breaks. Layer 2, the bridges, connections to outside frameworks, proved algebraically, rigorous, but with no claim to being ontologically primary. Layer 3, the sketches, plausibility explorations, consciousness, DNA parallels, cosmological analogies, clearly labeled as sketches, never as proofs, and nothing in layers 1 and 2 leans on layer 3. Negative results count as legitimate outcomes. Anyone who only ever publishes their wins hasn't understood the method. Slide 46. A piece of exact algebra. There's a matrix, A Greek X, with a beautiful property, A Greek X cubed equals 1 minus Greek X times the identity matrix. Its determinant is exactly 1 minus Greek X, and the fractal dimension df equals 3 minus Greek X shows up as a linear spectral dimension. Exactly proved, that's layer 2. 6 external bridges were tested against other researchers' frameworks. And here's a model negative result. Lobbed honestly, one bridge gave a frequency, nu m, of 8.23 terahertz, but that turned out to be a thermal vacuum scale, around 395 Kelvin, not a quantum gravity signal. A separation of regimes, not a contradiction. A numerology filter even threw out the framework's own tempting dark energy fit as statistical noise. Dimensional change here follows 3 operation types, call them type 1, 2, and 3, which together dissolve a whole family of fake paradoxes about whether information gets lost. Slide 52. A theory you can't kill isn't science, so let's name the kill conditions. FFGFT would be refuted by a lepton mass ratio drifting outside the rational invariant structure, a confirmed violation of the 2/3 ladder across sectors, Bell statistics deviating from the topologically carried correlations, or a Casimir force at subplunk distances landing outside the T0 prediction. On the philosophy, the 4-dimensional description is fractal, open and recursive, completeness is not claimed, auditability is. As one document puts it, what cannot be visualized is not therefore unintelligible. Structure and consequence outrank imagination. And the correction register isn't a flaw, it's a feature. Every recorded error is an error that can't be repeated. Slide 62. So, to land the plane. 1 parameter, Greek X, 1 geometry, the torus, and auditable consequences all the way down. We traveled through 6 parts, foundations and units, the Lagrangian and the fields, particles and constants, the quantum sector, methodology and validation, and finally dialogue and outlook. Whether you end up convinced or skeptical, the invitation is the same. It's all open, all versioned, all checkable. Go and check it. Thank you for watching.
Okay, thank you, Johann. Let me just allow the participants to... Actually, you are all allowed to unmute yourself and to start the video. I don't know how this is possible, but this is already selected. So do you want to take any questions at all? Because you are happy to. So I was just wondering, this FFGFT model, is it published anywhere? What's the situation?
Yes, I have some books on Amazon, also about it. Books are available.
But not articles like
But
citable, sort of
no,
like peer
no peer
reviewed.
review,
Okay.
nothing.
And you referred in frequently in the presentation, you are calling some documents by numbers, document number 139 and so on. What does it mean? What are those?
I have so many documents, so I have numbered them for easier.
So that's your own reference system to your own documents. Are they stored in some kind of repository, or what? Where can we find them?
Yes, they're in the repository. They're stored in the repository on Zalando.
Right. Thank you, Johann. And this is a long time work, isn't it? You worked on this for how long?
Oh, the ideas go back to 30 years.
All right.
I started
Wow.
on it.
Okay, this is a long time effort. Any questions, please? Look, I see Rocco with a hand up. Any questions, please? Here, Rocco, you should be able to.
I don't have questions. If no one else wants to have any question.
Yeah, I don't know why, Rocco. You should be able to unmute yourself, Rocco. I can't. Yeah, I gave you permission already.
Okay. Do you
Yeah.
hear me?
Yeah, we can hear you. Yeah.
Okay. So it's just a general understanding of the presentation. It seems to me that according to John, there is only one geometry which is useful for the idea of the simulation, and this geometry is based on torus geometry, isn't it?
Yes, it's right. It's a torus, and everything is are standing waves in different combinations.
Okay, thank you, John. That's all.
Okay, in that case, thank you again, Johann, for your presentation. I'm inviting our next speaker, Jeff Dillon. Jeff, I already made you a co-host, so you should be able to share your presentation and your screen. The title is a coincidence-based search for low-energy infrared photons in electron-positron annihilation. I'm quite familiar with this. Jeff and I, we are actually collaborators on an article. Jeff, I need to apologize. I've seen your emails and everything, but I was on leave. B, this conference organization and everything else took all my time. Let's pick up on this next week, if that's okay.
Yeah, absolutely.
Yeah.
Which is probably a good idea anyway, because in preparation for this presentation, I found a bunch of additions, let me say,
Right.
that I can add to the paper. So yeah, preparing
Anyway,
for this.
a
Yeah, go
huge
ahead.
welcome to our conference, and looking forward to listen to this. It's a
Yeah.
topic quite familiar to both of us, obviously. So
Yeah.
I'm going to, if you are ready to share, I'm just gonna
Yep.
mute myself, and I need 5 seconds to start the recording. That's all.
Okay, sounds good. Let me share. Oops.
All right, it's coming up.
There we go.
So I'm just gonna, I need 2 seconds, yeah?
Okay.
Yeah, you are good to go. If you go full screen again, that would be good.
Okay, we'll
Yeah,
do.
thank you.
Yep. 1 second. Okay. There we go. How's that? All right. Okay, I think we should be good. Well, thank you and welcome everybody. Thanks to IPI and Melvin for having me. I'm Jeff Dillon. I'm a former master's in physics student at the University of Washington, and I'm actually now looking at the PhD program at the University of Portsmouth. Excited about that. So this paper and this presentation represents a joint effort along with our gracious host, Dr. Melvin Robson, whose mass energy information principle motivated the experiment actually, and Javier Buenafe, who built the analytical framework behind it. I hope I'm pronouncing his name right. My own role in this experiment is on the experimental side, which includes the Giant force simulation and the Doppler boost strategy that uses a positron particle accelerator. And I have to be honest, some of the deeper theory in all this is above my current understanding. So I'll just kind of focus on the parts that I am familiar with. So what we have here, this proposal is preparatory. It's simulation for study. We take the mass energy information principle as a premise. We just make the assumption that the effect is real and ask what apparatus would be needed to verify this. The beam energy, detectors, timing, and the background rejection. It's an expansion of the protocol Melvin published in 2022 into something you could actually build. I keep the established physics, the quantum electrodynamics, relativistic kinematics, and detector responsers strictly separate from the speculative part, which is the informational photon itself. So to be clear, this is not a discovery claim. We're not quite there yet. We're on the road. The signal in the plots are simulated, not observed. It only demonstrates that the apparatus should be sufficiently sensitive once if it were to come online. I'm not claiming that the particle exists. I'm not offering a theory why it should. But on the bright side, even a no result would be useful, as it would set the first measurable upper limit for the photon energy. It might exist at a lower energy, so we're still checking that. So quantum electrodynamics leaves really no room for an extra low energy photon in annihilation. And that's why detecting the informational photon would actually be new physics beyond QED and the standard model. So the big idea. So the starting point is Landauer's principle, which states that erasing a bit of information has a real energy cost. Would be Boltzmann constant times temperature times the natural log of 2. Probably most of you are familiar with that, KBT, ln2. And that's been confirmed experimentally by others, by Beirut in 2012. Melvin's MII principle goes further and says information is physically real, and it's a mass-bearing property of matter. The testable consequence is the box on the right. So right now, electron-positron annihilation is the cleanest information erasing process we have in the laboratory, where two particles with definite quantum numbers vanish completely, leaving only radiation. Standard QED says exactly 2 511 keV photons result. This is well known. The MII hypothesis says that the erased information should show up as an extra low energy photon. Our benchmark is about 0.03 electron volt. And I want to just stress that's a design benchmark, not a firm prediction. What the real energy is remains an open question, and I'll come back to that at the end. So this is the part I like. So in talking with Melvin a couple of months ago, he mentioned the term a whisper at a rock concert. That's what we are looking for. So and why it's hard that the 0.03 electron volt signal is exactly right at the thermal quantum temperature at room temperature. It's the actual value is Boltzmann constant times room temperature is 0.26 eV, right where our IR photon, if it existed, well, I'm going to say when it exists, is going to land. Practically, that means that every mode in the band we care about is already occupied and just swamped by thermal photons, making it incredibly hard to detect. Every warm surface in the lab goes right where we need to look. The phrase I like to use is like listening to a whisper at a rock concert. On top of that, we have detector dark counts and beam backgrounds. And take a look at the spectrum. I mean, we're measuring a soft 0.03 electron volt photon in the same apparatus that a 511 keV gammas appear 8 orders of magnitude apart. And we got to measure them both and correlate them time-wise. And so dynamic range here is the real engineering challenge. So here's the plan we have. Our answer is three techniques that multiply together. So first of all, I got the design team together late last night. That would just be me. And we found that the original accelerator potential was way too low. I was a bit naive in my original design. I thought that this apparatus could be built in a university lab, almost a tabletop apparatus. You're going to see a little bit later on that that is not the case. So you'll see a lot of slides like this one that shows 5 MeV, 5 million electron volts is the particle accelerator voltage. That's been changed, and I'll explain more in a minute. We're going to be going to 150 MeV, and again, I'll explain more. So anyway, talking about the piece that I contributed to this process is the Lorentz boost, the particle accelerated. So where you fire a few MeV, or in this case, 150 MeV beam at a fixed target, and then the signal gets Doppler shifted up the high energy short wavelength side of the thermal radiation spectrum. We're trying to get away from the thermal background. So we have 3 techniques to do that. Again, I have 5 MeV in the slide, but that has changed to 150 more on that later. So speaking of the 5 MeV in the slide, it provides a factor of 4.6 in energy, roughly 2 orders of magnitude fewer thermal photons per mode for free, no extra hardware. And the next one, and this was Melvin's suggestion, that we cool the apparatus with liquid nitrogen to 77 K, which drops the thermal occupation of the boosted energy by another factor of 1,000,000 and cools the background noise. And then another, also Melvin's contribution, is we bunch the beam, the incoming beam, at 500 megahertz and use RF lock-in. So a beam correlated signal stands out from the random dark counts. So no single trick is enough. Together they clear the noise floor. Liquid nitrogen is sufficient and more fertile and easier to work with than liquid helium. So we have these 3 pieces that we're moving together, that we're placing together in this experiment to be able to detect, this IR photon. So we've submitted this to a couple of journals already, and there was some pushback, I'll put it that way. It's positron electron annihilation is well known. They've been doing it for 100 years. And a question might be, why haven't we seen this before? Well, it's because the IR photon is so weak. It is incredibly weak. Nobody's looked for it. I mean, it gets lost easily by 1,000,000 times in the noise background. So nobody's looked for it, but it's there. And so I kind of went to town with the whisper at a rock concert analogy, and I'll kind of elaborate more here. It's kind of fun to think about. So imagine you're in a rock concert, loud screaming crowd, the band's making a lot of noise, and somebody clear on the other side of the Coliseum is whispering to you. No way you could hear that. So here's the analogy. So what we do first is you and your cohort that's across the stadium, you move to the highest seat in the stadium, way up in the nosebleed section. And that corresponds to the Lorentz boost, kind of a weak analogy, but let's just, bear with me. So that raises the energy level of the conversation, let's put it that way. Okay, so now we're going to cool things off. So no concert goers were harmed in the making of this analogy, but imagine this. So instead of using carbon dioxide in the fog machine up on stage, we swap out liquid nitrogen and we swamp the entire stadium with a fog of liquid nitrogen. So nobody gets hurt, but boy, do they get cold. And the noise really drops, as you can imagine. And so everybody's much quieter now, all right? And then finally, the RF lock-in. You've agreed with your cohort that to whisper, you wait for a drum beat, and you only whisper actually between drum beats. And that's the RF lock-in. That's the analogy of what we're doing here with bunching the beam. So when you bunch a beam, you're not blocking any part of the incoming positron beam. You're using radio frequency to speed up some of the positrons and slowing down some of them. And so they come out in bunches. They're all still there. But in this analogy, you ask your cohort to speak only on between drum beats. And you also ask them to only say one syllable at a time and repeat it 10 times, and then go on to the next syllable. So with all that sitting in the upper section, and with the fog chilling the crowd, and the person's only whispering between drum beats, you can make out what they're saying. So that's what we're doing here. Okay. So anyway, I had a little fun with that. Okay. Where am I in my slide? Okay. Okay. So here's the experiment. In this experiment from left to right, we have, and now it's a 150 megabyte, million electron volt positron beam, RF bunched at 500 megahertz with a 30 picosecond bunch. And then it hits a stationary target at the center. We would likely run an electron-only beam first as a control run, and then able to better subtract the background noise in doing so. And then surrounding the target is a spherical lanthanum bromide shell with silicon photodetectors. That's a mouthful. Those catch the two 511 kilovolt gamma rays that are typically given off, drawn back to back in green here in the diagram. And then downstream in the forward cone sits the infrared single photon detector. And because of relativistic beaming, roughly half the soft photons emerge within that 24 degree of the beam axis. So a forward detector is a natural place for that beam, or for that detector. The whole detector package lives inside a liquid nitrogen radiation shield and a vacuum vessel at about 80 K. And then along the bottom is the readout chain, the gamma coincidence, the RF phase lock-in, reference back to the buncher, and then the triple coincidence trigger. That is the trigger, the two hard energy gamma rays, a forward low energy IR photon, and then the right RF phase in excess. And what, actually standard quantum electrodynamics predicts. So a word on the kinematics. So, due to conservation of momentum, when a positron and an electron, annihilate, the two gamma rays that are resulting fly off exactly 180 degrees apart, almost, pretty darn close. That would be called recoil. So we first thought that the recoil evidence would, if we measured it carefully, would give us additional evidence that the soft photons are kicking the two hard gammas slightly off back to back, and we'd see that. But working the numbers didn't quite work out. at 0.03 electron volt, a soft photon carries only about 5 times 10 to the minus 8 of 511 keV gammas of momentum. Not much at all. So the gammas veer off at a straight line only by the same tiny angle. So for scale, ordinary annihilation is already off back to back by about 10 to the minus 2 radians just from the electron's motion. That's what angular correlation of annihilation radiation spectroscopy already does, well-known technique. And it measures exactly how far the gamma rays veer off back to back. So our recoil sits a million times below an effect that's already there and well below any detector we could come up with. The honest conclusion is that we can't detect by recoil. So what we do instead is we catch the photon energy directly in that forward target. And a slight timing coincidence with the gammas, what is it, 2 nanoseconds, picoseconds? Anyway, it's a short time. And then we catch the two, and then you detect the two back-to-back high energy gammas. And if you detect the IR photon at the same time, you know that they were created in the same event. And so then the Doppler boost and cooling that buries the thermal background. Okay. So about the boost itself, for a beam on a stationary target, the center of mass Lorentz factor rises with the beam energy, and a soft photon emitted forward in the center of mass frame gets multiplied by gamma times 1 plus beta. The table gives the numbers at, again, here we're sticking at 5 MeV. This changed late last night, didn't have time to change the slides or the simulation. So the gamma center mass is 2.4, so to speak. So the beta is around 0.9. And the maximum forward boost is about 4.65. That takes our 0.03 electron benchmark to around 0.14 eV, about 46 microns down to about 9. The red dash curve on the plot is the resulting lab wavelength. The shaded band is 8 to 14 micron atmospheric and a detector-friendly window. And beyond the energy shift, the emission is beamed half of the isotopically emitted photons and within 24 degrees of the axis. That's what justifies a dedicated forward detector rather than just trying to instrument a full sphere in the infrared. That would be unnecessary. So again, I was hoping for a 5 MeV, and I'm going to explain why I moved away from that in a minute. So we're planning to go now to 150 MeV instead. And that changed a lot because my first thought is I'd be able to use a local lab at the Triumph lab facility at UBC, University of British Columbia, which I'm in Seattle, Washington, so not too far from here. Another option would have been the University of Washington lab itself, but none of them have 150 MeV positron beam. The Stanford Linear Accelerator doesn't have one. The only really two in the world that have them are the positron injectors at the Large Hadron Collider, and then this one at the Italian Daphne Beam Test Facility, and they have one. They're actually doing an almost identical experiment and have been for about 10 years, and it's called PADRE, the Positron Annihilation into Dark Matter Experiment, PADME for short. And so that just all happened in the last day or so. So a lot going on, very exciting. So for the simulation, I use this is the Geant 4 implementation. So Geant 4 is huge, the word huge in French. It's an open source analysis and simulation software currently in use at the Large Hadron Collider and many other accelerator labs around the world. I'm actually a contributing C++ developer on the Geant 4 project. Love the app. It's very cool. On the left here is the core, the near spherical lithium bromide shell around the target, with openings for the beam pipe and for the forward and infrared detector. On the right is a full package with the liquid nitrogen shield and vacuum vessel, about 66 by 35 centimeters. So when I was doing this, of course, I was using, published papers and AI. I'm a big fan of Cloud Code. It's lithium bromide. I've never even heard of lithanthemum. It's element 57. I did not know that. But anyway, the name, it just sounded expensive. So I asked Claude, I go, we keep referring to the spherical shell, which is actually quite large, I go, isn't it expensive? And Claude goes, yeah, good call. And I go, is there any, and then also at the 5 MeV, the forward detector, I actually asked, are any of those like off the shelf? And it was nope. So the detector came to be at 5 MeV, but it's something we would have needed to construct from scratch. And I, basically go, so how much is that going to be? And they go, about $500,000 for the both of them. I'm like, what? Which is 10 times or more, 100 times more than I was, expecting. I was going to self-fund this. Well, probably not anymore. So anyway, we're moving to a different spherical detector, cerium bromide, which is already used in the PADME project. So if things work out and we can leverage the PADME facility, we get a lot of this stuff for free. So to be determined. Of course, we need to actually publish this paper first and make it citable and all that. That's a work in progress, so of course not quite there yet. All right. So here's how the lock-in works. This is the simulation results. This is the RF bunching lock-in at work. We fold every detector hit at the 500 megahertz RF period, a 2 nanosecond cycle. So this is a beam correlated signal that piles into a sharp spike at the time of flight phase around 1.7 nanoseconds. That's pretty close. So the noise, the dark counts in the stray thermal photons is flat because it's uncorrelated with the beam. 100 picosecond window around that spike keeps essentially all the signal while throwing away about 90% of the noise. Kind of handy. So this is the additional leverage that lets us dig into the signal, find out, what's dig into the signal out of what's left after cooling. So here's the payoff in numbers. The table is this cascade at room temperature. 8,000 background events to start. The lock-in alone knocks it to 400. And the lock-in plus gamma coincidence together bring it to 34, about a 335-fold reduction in noise. Gamma coincidence alone looks worse because it emits a different background mix. Its value is realized in combination. The plot compares room temperature against the cooled, boosted configuration. Cooling drives the thermal background to effectively 0. So all that's left is the dark counts, which the lock-in already handles. Plus, if we do an electron-only beam, there will be no annihilation. So we'll be able to measure the noise and subtract that during the experiment. So the combined signal to noise ratio climbs from 36 to 45. So I just to be clear, this is an injected signal at an assumed rate. It demonstrates sensitivity and background rejection. It's not a detection. And again, 150 MeV, these numbers will all change. So stay tuned. So 3 quick looks at what the signature looks like. On the left, the IR signal has a clean line at 0.027 EV. In the middle, the 511 keV gammas. In the spherical detector on the right, the timing, the gamma prompt peak, and the slightly delayed IR peak from time of flight. Put them together and you get the full signature, 2 511 keV gammas in the shell, plus 1 or 2 forward IR photons. The tight time coincidence phase lock to the beam. That specific phase lock combination is what we search for, a soft photon at a definite temperature tunable energy standing out as a line above the smooth background that QED itself produces. Okay. So what this we actually deliverable. The actual deliverable of this work is a sensitivity projection. And even if we don't find anything, both outcomes are actually scientifically valuable. If that information photon exists, we win. 5 sigma excess of these triple coincidences. Evaluated with the proper statistically significant tests, all systematic uncertainty included, is a discovery in new physics. That's the plan. And then direct evidence that information is physical. If it doesn't exist, at least we have set the first ever upper limit on the branching ratio using the expression at the bottom. So sigma 95 over integrated luminosity times cross-section times efficiency. Since the rate factorizes as luminosity times cross-section times branching ratio times efficiency, this is a mouthful, times acceptance, and the branching ratio is the one thing theory doesn't constrain. The design maximizes everything else. Note that the reach improves at higher rest frame energy because that's where the boost does the most work. Either way, we convert a philosophical proposition into a measured number. And so here we have the branching ratio of the infrared gamma. And this is where that projection is made concrete. This is a real reach curve, the 90% confidence upper limit we could set on the branching ratio as a function of the hypothesized rest frame energy for stated exposure of 10 to the 14th annihilations. That's 10 to the 8th positrons per second. That's going to be a little lower at higher energies, but it's still a win overall. For a 10 to the 6th second run with a signal efficiency of about 1.7% measured directly in Geant4. So 2 things to read off of it. First, the reach improves as you go into higher energy because the boosted signal climbs the Wien tail and leaves the thermal background behind. That's the thermodynamics spectrum climbing exponentially and leaves the thermal background behind until it hits the floor around 2 times 10 to the minus 9 by purely detector dark counts, which no longer depends on energy. Second, look at the gap between the 2 curves. Cooling to 77K reaches that dark floor near a 1/10 of an EV, well below where room temperature gets there. So even at the nominal benchmark energy, we're probing branching ratios in the 10 to the minus 8 range, the first quantitative bound anyone have on the channel. One caveat, and this leads to my last slide, this reach assumes signals properties, so that's where we'd reach if the theory delivers them. So again, I did get this slide updated with 150 MeV. So I mentioned that the candidate facility now is the Italian Daphne Beam test facility in Italy and their current positron annihilation experiment. It's a very interesting project. I just did some research last night. Its main objective is to search for signals in new particle candidates for composing dark matter. It's a dark matter search. To achieve this, Padme uses collisions between positrons and electrons, just like we're doing, that hits a very thin diamond target. We're not using diamond, but very similar. It's very similar to what we're doing. And basically, it's a direct cousin to what we are doing here. And Lecky has the majority of the equipment we need. So that's pretty exciting. So this is what the Padme facility looks like. Oops, go back there, right there. So clearly it's not tabletop 5, and it uses 150 MeV accelerator, positron, electron, and it looks like they have a magnet, beam bending magnet there. So yeah, it's a little more involved than I originally. I was a little naive at first, but still doable. And if we could leverage this equipment we're looking at, that would be awesome. So we'll see. So this is the most important thing I've learned from we looked into this and the journals, and we've received their feedback. The sharpest question wasn't about the apparatus itself. They were okay with that, but it was, about the signal. Any search is defined by 4 numbers: the photon's energy, how many there are, their direction, and how often. Pretty standard. For standard annihilation, the theory nails all 4. That's why it's testable. And the question, kind of in loose language, why hasn't this been seen before? And I kind of already touched on that because nobody was looking for it. And they're like hidden in the background noise and a million times smaller than you would even expect. So for the informational photon, if you look at the right column, the energy is benchmark, the multiplicity we assume, the angular distribution is open, the branching ratio is unknown. So, the reviewers were right to push back a little bit. So we're and that's what Melvin was talking about before the talk. We have some talking to do. We'll get there. We're going to lock down the theory, and then we'll get the numbers right. So again, just to wrap up, this is a preparatory design study and not a claim. We're assuming the MEI effect is real, and basically kind of reverse engineered. What would it take to see it? The whisper to rock concert problem is addressed by 3 multiplying techniques: the Doppler boost for about 2 orders of magnitude, liquid nitrogen cooling for about 6 more, and the RF lock-in for the dark counts that remain. Geant4 gives us about 235-fold background rejection and signal-to-noise ratio from 28 to 45 on an injected benchmark. So thank you for your time. I have my email there. And a quick shout out for a separate project not related to this talk, but it was mentioned in the IPI channel that so Melvin has created a series of 10 videos on thermodynamics, mass energy information principle. So I kind of took those videos and ran with it and created this learning site, very similar to what you might find on brilliant.org. It's got the video breakdown. It's a Jupyter notebook where there's Python code. You can launch it, and so you can experiment on your own. And also kind of a fun check your understanding, just like on Brilliant, where it asks you several questions on each topic, and a little explorer where you can kind of tweak the parameters for your understanding. So anyway, I just kind of wanted to just throw that out there. So anyway, thank you for your time, and open for questions.
Thank you, Jeff. Yeah, very nice. And I must say, what you've done with this IPI Learn is really a good job. There will be more videos coming up. I've been booked up and busy with all sorts of things, but I will put more videos there. It will be quite rich actually in content. The lecture series is on information theory, information physics. So for those of you that are not familiar, so I mean, Jeff explained already, but I just want to say it again so it's clear for everyone. Jeff took an interest in doing this experiment that I proposed in 2022 or 2023. I don't remember exactly when I wrote the paper. And obviously we don't have the money and we don't have the facilities to do it. So the idea was to design, do the simulations, do the design, do the theory, do everything else in preparation for the real experiment. When either we have the means to do it or somebody else takes the interest and has the means to do it, the money, the facilities, and they will have a baseline, sort of like a source, which is the paper we try to put out to start this. So that's the history. But when you try to publish a paper where it is an experimental design, but you don't show any experimental results, or you don't design anything. It's just an experimental design, but you actually simulate that, and the performance of that is not very trivial. And when you add the complexity of the fact that this is, as Jeff puts it, new physics or unproven conjectures, it makes it even more complicated to get an article through. It gets a bit of pushback. So this is where we are, and we need to see what we can do to actually. We will publish this. No worries, we'll publish, but it's a bit of hard work, with the editors and the reviewers and all that. But Jeff, I wanted to ask you why. So let me just let our colleagues use the microphone. Yeah, it's already actually allowed. Why do you need so high frequency for the lock-in? That's the first question. I'm not sure why you need so high frequency. And I'm also not very convinced. Again, I still don't understand why you need high energy positrons.
Right.
In the
Yeah.
original paper, I specifically said we need thermal positrons. The lower energy, the better. In fact, thermal energies. That was my initial approach, and it's quite detailed in the paper why. So
Right.
these two things, because we did that paper, but when I looked at the paper, actually, what I did, I looked at it from a aesthetic angle, sort of like I made sure the images are in the right place, equations are re-edited. I looked at the text, but the physics and the simulations, I didn't have time to actually look at in super detail what you did there. I assume they're okay, and everything is fine. But now that you did a presentation, I'm just wondering, yeah, is there a reason for these things? I mean, frequency of
Yeah.
the lock-in, it seems to me excessively high. I don't know why it's so high. And then what was the second? What was the second?
Yeah.
The energy of the beam. Yeah,
Right. The
I'm
Doppler
not
boost.
convinced these are totally necessary. So that's and then if anybody has, look, I see Boris there, and if anybody has any questions, please ask your question. You should be able to use the microphone. Thank you.
Yeah, all good questions. So first of all, the RF lock-in frequency, extremely high. I noticed that myself. So again, I will admit that I've been using Claude AI to help with the design on this. It was extremely high, and to be fair, the Daphne project, the PADME project, where they're doing the same thing, they're also using RF lock-in. They're just using 50 hertz. What did I say? Like, what did we have 50 megahertz or something? It was like way up there.
Yeah,
And
exactly.
so
I
yeah,
used
yeah.
for my
It's
lock-in detections, I used my the single rule that I look for is a frequency that is not a multiple of the mains frequency,
yep. Yeah.
because
So you're correct.
you get noise from, I mean, when I was doing laser lock-in detection for magneto-optic hair effect, for example, I noticed when the cleaner would come and start cleaning the corridors at the university, and the vacuum cleaner would be turned on, I would get white noise in my signal because of the vacuum cleaner. It would be picked
Hmm.
up. So I had to do experiments Friday night, weekends, late in the evening, when there were other complexities there, like floor flexing, students walking around and all that. But my only concern was the frequency being 77 hertz, 173, some prime number or some known multiple of the mains frequency, but not being very high. It can be studied whether it improves. It should improve the noise floor, sort of like the detection sort of like level, but it didn't. Yeah, it's not so critical, I believe. It's not, you need to make sure it doesn't clash with anything else around, like the mains frequency or other sources. But
Right.
being so high, I'm not sure is a critical. It's an added complexity that you don't need, I think.
Absolutely. Yeah,
Yeah.
as that was one of the design features, I might say, that I uncovered last night when I was reviewing all this. Yeah, like I said, the PADME research, their project uses a much lower lock-in frequency. So you're correct, 100%. So that's going to be changing. And to answer your question about why the accelerator at all. So that point was to raise the energy of the IR photons, because currently in the rest frame, they're right at the same energy as the background noise. So it raises the photon energy above the noise floor. So the three things that we're using, the RF lock-in, the Doppler boost, and the cooling, all contribute to raising that IR photon above the noise.
Yeah, I don't think we have time to debate this now, but we can pick
Yeah,
this
no,
up together.
I'm certainly
Yeah,
open to this.
because
Again, this is
it's
new
not.
territory for me, so
Yeah.
I'm kind of flying by the seat of my pants here.
Well,
So I'm not gonna try to defend too much right here.
no,
So
we pick it up next week. No
yeah,
worries. I
absolutely. I
see
look forward to it.
Rocco is with a hand up, and if anybody wants to ask a question, please go ahead.
Melvin, what I perceive is that from Jeff's words that cooling wins, but I also had the perception that you limited it to 70 Kelvin. This why?
No, it's not. It's not limited. So what happened? We try to detect infrared photons. I have a bulb turned on next to me now, a lamp. The coffee is next to me. The screen in front of me. Everything emits infrared. So you are trying to detect some specific photons that are embedded into an ocean of infrared photons.
Yeah, I know.
Yeah.
Exactly.
So if we cool,
Yes.
the cooling is for the detectors. I'm not sure what Jeff did there, but you need to cool the infrared detectors, okay, to increase the sensitivity level. So it's
The sensitivity.
yeah.
Okay.
So
Thank you.
I used, for example, in the past FTIR, so Fourier transform infrared spectroscopy, and I did some experiments where we were physically pouring liquid nitrogen into the detector to improve the detection of IR, signals. This is the only reason: is detector being cooled using liquid nitrogen or some other means.
Okay, now I understand.
It's not the sample. It's not the sample or the beam.
Okay.
It's the detector.
Another thing. This seems to me base research. Why are you oriented to something private?
What do you mean private?
Startup, for example.
Because this research will not make any money. It's not like NVIDIA coming up with the next kind of cheap technology or some new lithography like ASML or something, some new kind of technological application that will make money to someone. This research is fundamental research. It's not. I don't see how Jeff's experiment and what I proposed, the experiment I proposed. Yes, it is new physics if it's successful, but I don't think he will make any. I don't see how he will make any money. At least the experiment itself, he will just answer many things. He will new physics. He will answer many things, but he's not going to make any money. So if he doesn't make money for Elon Musk or somebody, they will not pay for it. It's as simple as.
So you are saying that only states can be involved in this kind of research?
To be honest, I don't think Jeff thinks you need mega facilities. I don't think what I have in mind is actually still a workbench type of experiment. I budgeted at around $500,000, to be honest. I don't think, but this is without. It's always the calculation you make home is very different to what you get at the market. Is You end up
Yeah,
spending
yes.
more. And this is without budgeting for technician time, researchers and all that. It's just parts, big experimental bits and pieces. With the inflation we have now and prices changing all the time,
Absolutely.
probably $500,000 is not realistic either. But initially, when I wrote the paper, I thought it's about $500,000. And this is based on what I knew about infrared detectors, about what I imagine with these positron sources. I thought it's just a simple. In fact, we have them in our student labs.
Anyhow, this is a very big step in this study. I mean, experimental study is a very big step into the evidence of the theory.
And even if it generates a negative outcome, it's still research, because at least it says, hey, we tried this, it didn't work, find out why, or look for a different methodology, or
Absolutely.
it's a result, yes.
Yeah.
So it has to be done eventually, but
Okay.
yeah.
Really, my compliment to all of you.
Thank you.
Thank
Rocco.
you. Thank you.
Any other questions? We're running badly over time. Any other questions? I see Boris is already here. So our next speaker, if no other questions, anybody? I would like to thank Jeff once again. Jeff, we pick it up later next week via email. I'm going to get back to you. Thank you, sir, for your presentation.
Thank you. Thank you, everybody.
And now I would like to
Thank you, Jeff.
I would like to welcome our next speaker, is Boris Kriger, all the way from Canada. Hi, Boris.
Hi.
So Boris, send me a pre-recorded video. I guess I'm going to play that, and then you stay live and ask questions at the end. Is that how we do it, yeah?
Thank you.
Thank you, Boris. So let me just work out my things here. I need a few seconds, you guys, to bear with me for a few seconds. So what do I do now? I need to play the video. Video.
Good evening, and thanks to Professor Melvin Robson and the Information Physics Institute for organizing this meeting. I am Boris Kriger from the Information Physics Institute in Gosport and the Institute of Integrative and Interdisciplinary Research in Toronto. I want to begin with a difficulty rather than a result. 6 quantities are in serious scientific use, and all 6 are called measures of information. Applied to the same object, they do not agree, and there is no accepted procedure for deciding which of them is the right one. That situation has stood for 70 years, and it is not usually treated as a problem. I think it is a problem, and I think it has a solution. The first stage of this talk sets out the difficulty and derives the solution from it. The second stage puts the solution to work at 3 physical scales that share no mechanism: color confinement in quantum chromodynamics, the formation of stars and galaxies, and the global topology of the universe. The third states what does not follow and what remains open. 3 results appear along the way, each with the condition that would overturn it. Why an isolated quark has never been observed, why the proton is stable, and why the Hubble tension may lie in the calibration of our distance ladder rather than in the expansion itself. One screen on where the material comes from, so that nothing later has to be taken on my word. Volume 1 derives the cosmological constant from the QCD sigma terms with no dark sector. Volumes 2 and 3 develop the closed spatial topology. Volume 5 is the topology of quantum chromodynamics and isotopology in 23 papers. Volume 6 is structural persistence in 18 articles. Volume 7 is the information substrate theory, and the first stage of this talk comes from it. Alongside them, a code of practice for measured and declared quantities, and 8 notes applying it to published papers, including my own. Every claim tonight is attached to one of these, and I will name the document as I make the claim. Here's the difficulty in its simplest form. Take a string of random bits. Shannon's measure returns the maximum available value. That is not a convention. The entropy counts how much of the next symbol cannot be predicted from what came before, and in a random string, none of it can. Gell-Mann and Lloyd's effective complexity applied to the same string, returns essentially zero. That is not a convention either. Their measure counts the length of the description of the regularities, and a random string has none. So we have two established measures, no error in either, and opposite verdicts on one object.
Take a completely random string of bits. Any attempt to measure its information content as a physical property immediately hits a contradiction. Claude Shannon's mathematical definition yields maximal information for this string. Every bit is a surprise. Because nothing can be predicted, every symbol carries full weight. Murray-Gell-Mann looks at the same string and calculates a value of near zero complexity. He sees a total absence of regularities, leaving nothing in the string worth describing. These results represent two different ways of questioning the same object. Both calculations are correct, yet they produce inverse values for what we call information. A linguistic drift has obscured the physics here. For 2,000 years, the word information described an operation, the act of giving form to matter. Modern usage has turned that operation into a noun, treating it as a constituent substance, like an atom or a field. Information names a property of the substrate, its differentiatedness. It measures the degree to which being is structured rather than featureless, requiring a specific descriptive access to produce a real number. We separate the physical substrate from these descriptive projections using a simple analogy, a human hand. A photograph extracts surface texture and color. An X-ray reveals the internal density of bone. A shadow preserves only the outline of occlusion. The hand exists independently of these images, yet each projection is mathematically true along its own chosen axis. Physics currently employs 6 such axes: channel, description, macrostate, cost, receiver, and regularity. They often produce contradicting values because they are looking for different types of structure within the same substrate. Intellectual discipline requires us to declare our projection axis before quantifying any system. For this analysis, we will use the axis of regularity. The regularity axis, or effective complexity, measures what recurs across an ensemble. It keeps the persistent pattern while discarding the specific details of a single instance. A perfectly ordered crystal is cheap to describe on this axis. Its pattern is a simple repetition of a single unit. A perfectly random gas is equally cheap. Since every configuration is typical, describing the ensemble requires almost no specific information. This chart tracks total information entropy, rising from order to chaos. The effective complexity curve instead rises, peaks sharply, and falls back to zero. This peak marks the intermediate regime, where separating a physical pattern from its instance takes the most descriptive work. Structural persistence holds a system at this peak. This makes effective complexity a diagnostic tool for identifying where the universe has accumulated lasting forms. We apply this diagnostic first to the strong nuclear force. Quarks carry a Peller charge, yet 50 years of experiments have failed to find an isolated color charge at any energy scale. The standard explanation assumes free quarks are valid states that are too energetically expensive to maintain. This treats confinement as a matter of budget rather than geometry. Reframing the color configuration space as a closed S3 manifold changes the physics. This is a finite space with no edge and no exterior region. On a closed manifold, asymptotic color flux is mathematically undefined. Without an outside for the field to reach, the free quark ceases to be a state. This geometry turns baryon number into a topological winding number. This shift explains the results from Super Kamiokande, which has seen zero evidence of proton decay across decades of observation. The proton represents the minimal non-trivial winding in this closed space. It remains stable because it has no simpler topological state to unwind into. Confinement topologically reorganizes the regularity of the strong sector. It preserves the confined spectrum's pattern while discarding the specific configurations of individual colored charges. Regularity accumulates across physical scales. Nucleosynthesis creates the substrate for stars, which forge planetary metals. Each level becomes a boundary condition for the next, allowing patterns to pile up. This chart highlights the decoupling of mass and description. Earth's biosphere is a tiny fraction of the universe's mass, yet requires over 6,000 bits to describe recurring patterns, genetic code, metabolism, and neural structures, holding over half the describable regularity of our cosmological model. A system's contribution to cosmic regularity has almost nothing to do with its physical size. The biosphere creates an extreme local peak on the regularity curve, even while remaining physically infinitesimal. In 1917, Einstein proposed a closed, finite universe. Willem de Sitter soon pointed out a problem with this simple sphere. It creates ghost images of every object, leading to the refined model of a projective elliptic space called RP3. This closed topology fixes the available field modes. It determines exactly which regularities can appear in the large-scale structure of the universe. The cosmic web behaves like a text with a highly compressible grammar. Its density states are more structured and predictable than DNA's spatial patterns. This structural grammar exists because the web occupies a unique mechanical regime. It allows volume to expand through its voids, yet its mass-bearing filaments possess a tensile resistance. It stretches like a string bag, which expands less than the tablecloth beneath it. This mechanical lag, epsilon, multiplies the mass fraction outside voids by the pion-nucleon sigma term. Resisting expansion by this factor of 0.0815, a ruler inside the web appears short, making background expansion look artificially fast. This structural lag matches the observed gap in the Hubble tension. The discrepancy arises as an artifact of measuring the universe with a ruler that is being held back by its own internal regularity. Quarks, biospheres, and cosmic filaments rely on vastly different physical mechanisms. They do not share a single optimization principle. They share a diagnostic. Effective complexity identifies the persistent structure required to hold a system at the intermediate peak of the regularity curve. This method demands we separate projection from substrate. Declaring the axes is the only way to compare descriptions across regimes, sharing no common physics. Without this discipline, the noun information access the phlogiston or our era, a placeholder word that silently obscures the very structural patterns we are trying to observe.
When we step back and ask what mass actually is, we quickly realize there isn't just one answer. There are several distinct operational definitions. First, we have inertial mass, which measures resistance to acceleration. Then, passive gravitational mass, describing how an object responds to a gravitational field. And active gravitational mass, which defines how it generates a field in the first place. Finally, in special relativity, we define invariant mass as a fundamental property of an object's four momentum. The first three agree to about 1 part in 10 to the 15th, but their equivalence is a profound empirical fact that required Einstein's general relativity to explain. It was never true simply by definition. When we look at where the mass of ordinary matter comes from, only about 1% is generated by the Higgs field through bare quark masses via Yukawa couplings. Roughly 99% originates from confinement, gluon field energy, and the trace anomaly. The mass of everyday matter is overwhelmingly dynamic binding energy, not fundamental substance. In general relativity, mass has no single unique global value. We rely on ADM mass at spatial infinity, Bondi mass at null infinity, or Komar mass in stationary spacetimes, while quasi-local mass remains an open problem. For this talk, this distinction is essential. The interception ratio later in this talk, sigma over m minus n, represents the precise fraction of the nucleon's mass derived from scalar quark content rather than gluon dynamics.
The rest mass of a proton exceeds the combined weight of its internal quarks by a factor of 50. If you add up the pieces, you only find 2% of the total weight. Standard physics attributes the missing 98% to the energy of a confining field, an invisible force holding the quarks together. Boris Kriger proposes a different reading of this data. He suggests that what we interpret as a confining force is actually a coordinate of admissible topologies. Under this principle, mass is simply the energy of the background vacuum trapped within a closed geometric shape. This theory separates mass into two distinct layers: a bulk count that accounts for 99% of the weight, and a 1% residual that contains the transitions of nuclear dynamics. This mechanism relies on self-connectedness. Imagine a particle not as a solid object, but as a knot tied into the fabric of space itself. A closed topology, like a spherical proton, locks a specific amount of vacuum fluctuation into a self-bound figure. That held energy is what we measure as rest mass. Rest mass represents the quantity of empty space held captive by a specific geometric closure. This data shows the mass of light nuclei from hydrogen to oxygen. To find these numbers, Kriger multiplies a single constant, calibrated at the proton, by the amount of vacuum the shape holds. This calculation reproduces the measured masses to better than 99% accuracy. Determining if these shapes are physical realities requires seeing what happens when the geometry is removed. In proton-antiproton annihilation, a geometric figure and its exact mirror image collide. When these coordinates coincide, the topology cancels to zero, the knot unties, and 100% of the trapped energy is released as radiation, leaving no residual mass behind. This total conversion suggests that mass-energy equivalence is a function of adding or removing topological knots in the vacuum. If shape counting explains 99% of the mass, we are left with a tiny fraction of a percent of unaccounted weight. Kriger argues that this residual is the entire active content of nuclear physics. As spheres combine into heavier atoms, they form more complex closures, torus, tetrahedrons, and cubes. These more symmetric configurations are more perfectly closed. They hold the vacuum tighter, which causes them to release a tiny drop of self-connectedness energy. This released energy is the binding energy that holds an atom together. Nuclear dynamics are driven by these transitions between different geometric shapes as they seek more perfect closure. This geometric drop is exactly the hidden mechanism that triggers nuclear fusion and sustains the life cycle of stars. It also explains the iron peak. Iron is the most topologically self-connected shape possible, making it the final destination for stellar fusion. The Standard Model requires 8 separate postulates to explain these same phenomena. Here, they follow as consequences of a single identity. The stability of the proton, the absence of free quarks, become properties of the topology itself. The wake and behavior of everything in the universe emerge directly from the underlying geometry of the vacuum.
Now let's examine the projection from the three-sphere, S3, to real projective space, RP3, and trace whose idea this historically was. In 1917, Einstein proposed a spherical space, S3, a closed finite universe where the cosmological constant, lambda, was introduced for the sole purpose of holding it static. That same year, de Sitter presented his empty universe solution and argued instead for elliptic space, RP3. His reasoning was that in a standard spherical space, every object would inevitably produce an antipodal ghost image. Between 1922 and 1927, Friedman and Lemaire introduced dynamic solutions. Spatial closure survived as a valid scenario, but over time it quietly lost out to spatial flatness, driven more by mathematical convenience than any actual physical refutation. This brings us to RP3, defined as S, 3 quotiented by Z2, a 2-to-1 covering formed by antipodal identification. It eliminates those ghost images, leaves a fundamental group of order 2, and remains fully orientable, unlike the 2-dimensional projective plane. In fact, this space is topologically equivalent to the rotation group SO3. Because this identification is strictly antipodal, parity becomes a core structural feature, ensuring that the 3 anisotropy channels cleanly separate rather than blur together.
According to standard linear perturbation theory, the universe is built on a homogeneous, isotropic background. As we zoom out to the largest observable scales, local gravitational poles balance out, and the peculiar velocities of galaxies should mathematically average down to zero. The Cosmic Flows 4 dataset maps the peculiar velocities of over 55,000 galaxies. Instead of decaying as predicted, the data reveals a massive bulk flow of matter that rises monotonically on scales pushing past 160 inverse megaparsecs. This map displays the cosmic microwave background dipole, the bipolar temperature gradient caused by our own movement through space. When we compare this kinematic baseline to extragalactic source counts, like the Quaya quasar catalog, we find a cosmic matter dipole that exceeds our expected motion by 5 standard deviations. Deep imagery from the JWST JADE survey reveals an additional structural asymmetry. As we look further back in redshift, bararcational direction, or chirality, of spiral galaxies shows a statistically significant bias toward one-handedness over the other. When we plot the direction of the cosmic flow's 4 bulk flow, the C-crest matter dipole, and the CMB's quadrupole-octopole alignment, often called the axis of evil, on a celestial sphere, they all cluster within a 12-degree radius on the sky. The standard cosmological model treats bulk flows, matter dipoles, and parity violations as entirely separate phenomena. Because the equations lack a mechanism to connect them, these observations are typically dismissed as independent systematic errors in their respective data pipelines. The strict alignment of these specific structural anisotropies across entirely independent datasets points to a singular geometric origin in the fundamental architecture of the universe. An alternative framework resolves this by defining the spatial topology of the universe as a real projective 3 space, denoted as RP3. This is derived from a 3-dimensional sphere mathematically quotiented by a Z2 antipodal identification. The Z2 identification connects every point on the sphere to its exact opposite. This mapping explicitly breaks pure global isotropy by establishing a preferred topological axis directly into the geometry of the space. To maintain stability and comply with the Banach contraction principle, this manifold is subject to a dynamic constraint. It is equipped with a double counter-rotating configuration across 2 orthogonal planes. Modern theoretical physics rests on a pervasive assumption. We treat the universe as a vast grinding machine that stores information as physical bits and actively computes its own evolution from 1 microsecond to the next. This framework is built on a foundation of rigorous theoretical limits. The holographic bound links a region's entropy to its surface area. Unitary evolution dictates that exact quantum data is conserved over time. Landauer's principle assigns a physical thermodynamic cost to erasing a bit. Because these mathematical limits are so precise, physicists, most notably John Archibald Wheeler, inverted the relationship. They declared it from bit. Information went from being a tool we use to measure reality to the actual physical substance, the hardware of reality itself. Treating information as the fuel of the cosmos is a mathematical category error. It conflates the axes we use to measure the world with the underlying nature of the world itself. Theoretical physicist Boris Kriger designed the information substrate theory to dissolve this exact error. Under this framework, information is not a fluid, a force, or a conserved quantity. It is simply a name. It is the term we use to describe the differentiatedness of being. The reification error occurs when we take quantitative properties that belong strictly to mathematical projections, like time, entropy, or computational cost, and assign them to the timeless, axis-free substrate of reality. The universe needs information in no form. It stores no bits, it computes nothing, it contains no information mass. It simply cannot lack differentiatedness. To understand why the universe is differentiated, we have to start at absolute mathematical minimums. The logic is straightforward. Absolute nothingness is logically impossible. A total void cannot sustain its own obtaining. Because true nothingness cannot exist, whatever does exist must possess distinctions. If a state is completely undifferentiated, if there is no telling anything apart, it is indistinguishable from the null state. Therefore, being must inherently be differentiated. This leads to the formal minimal model of the substrate, abstract nodes defined only by the identity relation. Node A is simply not node B. Notice what is missing. This substrate carries no metric, no clock, and no coordinate geometry. It possesses no quantifiable amount. The universe does not run on a supply of information that could ever be depleted. Differentiatedness isn't a resource you can spend or store. It is an ineliminable condition of existence. To get a measurable number, you have to apply an axis. You take the raw substrate and perform a surjective reduction. You cast a shadow of the substrate onto a specific coordinate crane. This is called a projection. When you reduce the substrate along the channel axis, isolating only probabilistic outcomes, you extract Shannon entropy. When you project it along the macrostate axis, isolating the count of microstates, you extract Boltzmann entropy. Project along the description axis, looking for the shortest possible algorithm to reproduce a structure, and you extract Kolmogorov complexity. The cost axis yields Landauer's thermodynamic limit. The receiver axis yields Bateson's qualitative difference. Each individual projection theory is mathematically correct, but only because it retains the distinctions of its chosen coordinate while aggressively collapsing all the rest. The fractured formalisms of information theory are actually discrete projections of one substrate, and the substrate itself is in the domain of no projection measure. You cannot ask how much information is in the substrate, because amount is a property of the shadow, not the object. This framework directly dismantles the idea that the universe acts as a physical hard drive. The holographic bound is a strict limit on the macrostate projection of a region. It dictates the maximum value of that specific shadow. It does not mean the internal volume is filled with physical bit stuff. The same logic applies to the idea that the universe is a processor. Computation requires steps. It is an inherently time-dependent operation. Time is simply another axis. Applying a temporal predicate like computing to the timeless substrate is a direct category error. Physical subsystems within the time projection compute to recover lossy data, but the universe as a unified whole computes nothing. We can see the utility of this theory by applying it to the ultimate stress test, the black hole information paradox, originating with Stephen Hawking. The paradox describes a stripped physical conflict. Quantum mechanics says exact data must be conserved, but black holes appear to destroy that data, emitting only a featureless thermal spectrum as they evaporate. The information substrate theory neutralizes the physical destruction narrative. The timeless substrate loses nothing because it never held a physical informational substance to begin with. Instead, the paradox is a mathematical tension between two competing projections of the exact same underlying process. The unitary projection demands exact evolution, while the macrostate projection demands a thermal spectrum. The task is not to track down a physically leaking fluid. The open question is how to map the joint structure consistency of these two specific mathematical reductions. John Archibald Wheeler was correct about one thing: distinction and observation are constitutive of modern physics. His mistake was the inversion. He made the projection axis quantity, the bit, the fundamental ground of reality. We have to keep mathematical limits strictly within the domains of their projection axes. Theoretical physics must stop demanding the universe compute, store, or physically manifest our equations. The universe simply is an axis-free, perfectly differentiated substrate. In 2022, physicist Melvin Vopson proposed the second law of infodynamics. He suggested that physical systems naturally evolve by minimizing information entropy, favoring structural complexity and organization over time, rather than decaying into disorder. Theoretical physicist Boris Kriger has now proposed a formal solution. His work demonstrates that this tendency toward structural complexity can be derived directly from the laws of quantum chromodynamics, the framework governing the strong nuclear force. The ultimate test lies in data from the Dark Energy Spectroscopic Instrument, or DESI. It provides a massive, high-fidelity map of the cosmic web. Testing this QCD derivation against the DESI galaxy catalog provides a way to determine if cosmic structure is intrinsically informational or simply the result of random distribution. To measure information entropy, we must process the cosmic web as a raw bit stream, moving past the standard astronomical treatment of galaxies as simple point masses. This requires spatial voxelization. Researchers projected the coordinates of 11,809 galaxies into a three-dimensional grid, dividing the survey volume into blocks. Each block is assigned a discrete state based on its density. These categories range from state 0 for empty voids to state 5 for rich clusters. The result is a spatial sequence of discrete symbols, a text written in a 5-letter alphabet. By converting the galaxy distribution into these discrete symbols, we can mathematically determine if the universe possesses a consistent internal grammar or if its structure is unpredictable noise. The first test applied to the DESI data is algorithmic compressibility. This measures the regularity of the data by seeing how much its description can be shortened without losing information. This chart compares the compression ratios of different density fields. At a resolution of 40 megaparsecs, the actual DESI galaxy distribution is 18% more compressible than a random model of the same density. The second test measures mutual information. This quantifies the spatial predictability between adjacent cells in the grid. In a random field, knowing one cell's state tells you almost nothing about its neighbor. In the DESI data, spatial predictability is 680 times higher than that random baseline. This indicates the presence of strict rules governing which density states can exist side by side. To map the vocabulary of the cosmos, researchers analyzed 2 by 2 by 2 voxel blocks as 8-symbol words. While there are over 390,000 possible ways to arrange these blocks, the actual universe utilizes only 0.13% of that available vocabulary. The empty block, representing the cosmic void, dominates the distribution. This frequency distribution is the signature of Zipf's law. Zipf's law emerges in systems, including human languages, that are optimizing for a specific trade-off between competing constraints. This graph plots the frequency of density patterns. The cosmic web follows a Zipf distribution with an exponent of 1.29. This is mathematically steeper than the distribution found in English or Mandarin.
Back at the start, we had 6 measures contradicting each other, all called information. They are not rivals. They are 6 projections of one underlying substrate. The contradiction was never in the world itself. It came from assuming a single quantity was being measured 6 different ways. Effective complexity is simply what differentiatedness looks like along the regularity axis. When you declare your axis, you can meaningfully compare descriptions across scales and regimes that share no common physics. Leave it undeclared, and it quietly replaces the real mechanism with an illusion of unity. That methodological discipline is the true transferable takeaway of this work. Thank you very much for your time and attention. My contact details and references are on the screen. I would love to hear from anyone working on estimators, and especially anyone who wants to challenge the topological premise. It was declared explicitly so it could be tested and critiqued. Thank you again, and goodbye.
Thank you, Boris. Beautifully narrated, nice presentation. We still have some people online. Any questions for Boris, please? Wait a second. Okay, I opened up the microphones and cameras to everyone. If anybody has any questions for Boris, please feel free.
Thank you so much for your patience to listen and watch. I understand it's a huge volume of information.
Yeah, it's at this time of night. I don't know what mass is anymore, to be honest. I'm going to sleep. I'm gonna, yeah, I don't know what I'm gonna think about, but it's, yeah, it was heavy.
You will be dreaming about the topology of the universe.
Exactly. Okay, questions, please.
Anyways, thank you very much. It was, when I watched it myself now, I think it's very complicated and it sounds like not very substantiated, but it is very much substantiated in every particular detail that I have been discussing in this presentation. It's just otherwise, if we do not look in the general view of the things, it will slip our attention and understanding. So if anyone interested in any particular details, they are usually listed in particular papers. and we can discuss every particular part of the presentation that we were talking about. Thank you.
Sounds good. And Boris is also a member of the IPI, so if anybody from IPI wants to get in touch with Boris, he will be on the group IPI group discussions, and I can provide the email as well if Boris allows me. Are you okay if anybody? Yeah. When I put the videos online, I'm gonna have video description, and I will list your institute, Boris, with the website and everything. Is that okay? So people can find you. Yes. But overall, I think we should be able to agree to disagree. I think we should remain open to. Nothing is settled. Okay, let's put it like this, especially in this area of research. So we should be able to debate and freely discuss ideas, criticism.
I'm not sure that we are disagreeing. It's just all about the definition of the information and definition of mass. I've shown in my presentation that both are very undefined and can be defined in at least 6 or 7 different ways.
That's right.
So
I
that's
totally
why
agree.
I've shown in the end that actually I do not contradict you. On different levels, I've shown that actually the information is equivalent to mass, because when vacuum actually makes the confinement within the proton, it stores the C quarks from the quantum vacuum, and it makes the unit of the information.
Yeah.
So mass here is absolutely equal to the information that
Boris,
is.
don't get me wrong. I actually welcome criticism. To be honest, I think it's healthy. I think it's important, and I think we should be able to criticize and debate science freely. Nothing is settled. Nothing is settled, and especially when we don't have empirical evidence on many of these things.
Those are absolutely
exactly. So I'm super happy with this. Otherwise, there is no progress. Okay, if we can't.
The confinement is very well known and have been shown in the accelerators. Pions are bombarding the protons, and we see that we are getting this C quarks, which is taken from actually the quantum vacuum. So usually I'm basing everything I do on the experiments that are well proven. Also, I maintain the connection with everybody who was actually doing those experiments, who is alive still, and they actually answer me.
But I was talking about my work and the experiments that haven't been done to confirm some of the the work I put forward. So I wasn't referring to your presentation. I was referring to my own. That is open for valid criticism, is open for debate, is unproven empirically. This is what I was trying to make the case.
I think you have a brilliant intuition that I bring the proof on all 3 levels of the scale, on the quantum chromodynamic level, on the level of this web of the galaxies. I have shown that they are organized more orderly than the language. Can you imagine that?
No, it's powerful.
As a result. And
I
then
totally agree.
the whole universe, as I've shown that there is a topology which is so interconnected, this RP3 sphere, that actually also is proven that instead of flat universe as in LCDM model, we have here the very well organized system. So you are right. It's just doubtful that you can actually prove it only on the level of a small experiment. I think it is proven on different scales in different ways. All right.
And this is why I want to talk to you next week, or as soon as
And
possible.
also without a very careful definition of both things, information and mass, what do we mean by it? Without that, actually, any experiment that you do might be not convincing, because someone will come and say, oh, this is not mass, or this is not information, and so on.
Yeah. Complicated stuff, really complicated stuff.
All
So
right,
thank you, Boris. Very much appreciated. Thank you, sir. So we are officially 1 hour over time. Our last presentation in this oral session too is from Yalitza Ramos. She gave me a pre-recorded video. I was wondering if she's with us now. Let me just check. I don't think she's. Yalitza, you are not here, are you? Because what I'm thinking I have the recording is going to be on YouTube, but I'm thinking to skip that. We are 1 hour over time. The reason is her presentation, she changed the title. Okay, so what I have in this conference agenda, it doesn't match with the title of her video recording presentation. So because we are 1 hour over time and because this doesn't match, I'm thinking to close this first day here. And I will play Yalitza's video. I will just upload it on YouTube as part of the conference, but not live now. I would like to thank everybody for staying so late. People, I apologize to people that are watching on YouTube. I'm running this on my own and this is really exhausting. I can't really go and take any comments from YouTube or any live questions and put to our speakers. It's a lesson that I learned. Probably next year I'm going to have some kind of conference committee or some kind of team running this, because on my own is not very practical. Actually, it's quite challenging. But anyway, good evening, everyone, or good afternoon, or wherever you are. Thank you so much. I'm going to close this session, and we reconvene tomorrow at 5 p.m. with day 2. All the best, and thank you very much. Bye, everyone.